Have you ever wondered what it's like to see the world through someone else's eyes? For people living with neurological conditions that alter perception, the experience can feel utterly alien, like looking at a familiar scene but struggling to make sense of it. Today, we're diving into a groundbreaking project that's redefining how we understand these invisible challenges. Imagine a world where doctors, caregivers, and researchers could experience conditions like simultanagnosia, where the brain can't piece together a coherent scene, or prosopagnosia, where faces blur into strangers. That's exactly what the Perceptual Reality Transformer aims to do. This framework uses advanced AI to simulate 8 distinct neurological perception conditions, acting like a virtual reality headset for the mind. Except instead of games, it's helping us step into the lived experiences of others. At its core, the system relies on 6 neural networks, each designed to mimic how the brain processes visual information in unique ways. Think of them as specialized tools in a neuroscientist's toolkit. For example, one network might distort spatial relationships to simulate simultanagnosia, while another introduces visual noise to replicate attention deficits. The key innovation. These models aren't just generating random distortions. They're grounded in clinical data, translating real-world symptoms into precise algorithmic behaviors. Now, how do these networks actually work? Let's break it down. Researchers tested a range of models, from traditional convolutional networks, think of them as the early adopters of AI, to cutting-edge vision transformers. The results were revealing. Vision transformers, or ViTS, outperformed other architectures in tasks requiring global context, like reconstructing scenes for simultanagnosia. Why? Because they're better at understanding the big picture. While CNNs focus on local features, ViTS analyze relationships between elements, making them ideal for simulating conditions where the whole scene is distorted. Imagine trying to solve a puzzle where the pieces keep shifting. That's what it's like for someone with ADHD-related attention deficits. The AI models add random visual distractions to simulate that fluctuating focus. For depression, they dim colors and reduce contrast, mirroring the visual fog reported by patients. And for anxiety, they create a tunnel vision effect, narrowing the field of view, just like the classic spotlight metaphor. Each simulation is calibrated using data from real neurological studies, ensuring accuracy. But this isn't just about cool tech. The researchers grounded every simulation in clinical data. They studied real symptoms, like the slowed processing in simultanagnosia or the face recognition gaps in prosopagnosia, and turned them into precise algorithms. It's like giving AI a textbook on human perception, except this textbook is written in code. The results? Vision transformers outperformed other models in every test, from reconstructing images to scaling severity levels. But the study didn't stop there. They tested how well these models generalized across different datasets, like ImageNet and CIFAR10. The EncoderDecoderCNN and ViT models showed the most consistent performance, adapting smoothly to new image types. In contrast, diffusion and VAE models struggled with consistency, highlighting the need for specialized architectures in this domain. Here's where it gets really interesting. Some models excelled at specific tasks. For example, generative VE offered a nice balance between quality and flexibility, letting users tweak hidden layers to create different effects. But others, like DiffusionPerceptual, which is usually great for generating art, faltered here. They had trouble reconstructing images accurately, and couldn't reliably control the severity of the simulated condition. This suggests that standard AI tools might need major tweaks to handle these complex tasks. And the applications? Oh, they're huge. Imagine medical students experiencing what it's like to have prosopagnosia, face blindness, or anxiety tunnel vision through these simulations. It's not just about learning facts, it's about feeling the challenges patients face. The study also found that conditions like depression required careful calibration of lighting and mood, proving that AI isn't a one-size-fits-all tool. It needs to be tailored to the human experience. Of course, there are limits. Right now, these simulations are visual only. But neurological conditions often involve more than sight. Think of how sound or touch might play a role. The researchers are already thinking ahead, suggesting future work could include multisensory experiences or dynamic, evolving simulations that change over time. So what's the takeaway? This work isn't just about AI, it's about empathy. By making atypical perception tangible, we're not just advancing technology, we're building bridges between diverse human experiences. Whether it's improving medical training, fostering compassion, or pushing the boundaries of AI, this project shows that the most powerful tools aren't just smart, they're human.